3, 2, 1, Dr. Peyam. Hello! And thanks for watching. And today I want to do something really cool as usual. So I don't know if you watched 3 Blue 1 Brown's video on collining blocks and how he wants to calculate pi with it. If you haven't watched it, you definitely should watch it. It's such a beautiful video and it involves some very neat geometry using arc length. And I watched it, I was amazed, okay? So definitely watch it. But what happened then the next day was a subscriber of mine, Tobias Schmale. He gave me a solution of the same problem using linear algebra. And I saw that solution and I was like, it's too beautiful not to teach. So let me give you an alternative solution to the pi collision block problem. And if you don't know what the problem is, let me remind you of what it is. So step 0. And I got a new blue pen just for that. That's how much I like that solution. So here's the setup. Suppose we have 2 blocks of 2 different masses, where we have a huge mass here, capital M, and a smaller mass, little m. Smaller mass, okay? And so we have 2 masses at points x1 and x2. So 2 masses, little m and big M, with x1 less than x2. And moreover, suppose there's a wall at 0. Okay, so here's we have a big wall, infinite mass, okay? And moreover, suppose initially M does nothing, so the initial velocity is 0. So M rests. It's like in courtrooms, like the courtroom rests or something. And therefore, initially we assume that V1 equals to 0. And moreover, suppose that the big mass moves towards the smaller mass with a velocity, let's say V2 equals to -1. Then what happens? Because this is standing still and this mass is moving to the left, at some point it collides. Bang! Okay? It does that, and then because of this collision, this mass also moves to the left and hits the wall. So bang! It hits it again, and then it goes back to the big mass, which hits it again, and it hits the wall, hits it, and it hurts, you know, that poor little mass, okay? And the question is then, how many total collisions are there? And surprisingly, this answer has to do with pi. So there's no, it's a complete coincidence. It seems at first that pi appears, but, well, pi is everywhere. So even in the food you eat, apple pie. That's why it's good. So the question is then, how many collisions? And by collisions, I mean the following. Not only the collisions between the masses, but also the collision between little m and the wall. So how many collisions happen before this big mass goes home? So before capital M goes to infinity. So, and notice the only way this could happen is if this mass moves to the right way faster than this mass. Because then this mass tries to catch up, but it can never hit it. So that is V2 is greater than V1. So that was the question 3 Blue 1 Brown tried to solve, and the beautiful answer is it has to do with pi. And by the way, for greater animations, please watch his video. It's hard to do it by hand, but I'm doing my best. Okay, so we have that, and then In 3 blue, 1 brown, he gives a beautiful solution using geometry, and Tobias Schmale, which by the way, I love that name because it sounds like Stephen Smale, who's a Fields medalist at Berkeley and who did dynamical systems. So what are the chances? So Tobias Schmale gave me a solution just using linear algebra. So if you know linear algebra, this is super neat, doesn't require any geometry, just some pure algebraic computations. And I hope you love it, because I did. So, first of all, let's try to come up with some equations. So, now, suppose those two masses collide. So suppose you have something like that. This m with velocity v2 moves towards little m with velocity, let's say v1, be like this, v1, and then they collide. Then after the collision, so after bang, the big mass and the small mass have different velocities. And we call those v2 prime and v1 prime. And we're only talking about collisions between blocks. Then it turns out those two velocities and those two velocities are actually related by what's called conservation of energy. Because conservation of energy tells you that the kinetic energy, I think that's what it is. So m v1 squared plus m v2 squared is the same thing but with primes, equals to m v1 prime squared plus m v2 prime squared. And again, in other words, before they collide, their velocities v1 and v2. After they collide, they have other velocities, and it turns out this kinetic energy is conserved, which is a neat way of finding v1 prime and v2 prime. And similarly, we have conservation of momentum, which tells you that the sum of momenta are conserved as well. So mv1 plus capital mv2 equals to little m v1 prime plus capital M v2 prime. And careful, those are not derivatives, those are just, velocities after the collision. So v1 prime, v2 prime are velocities after the collision. And here comes the neat thing. From those two equations, it's actually possible to explicitly solve for v1 prime and v2 prime in terms of v1 and v2. And the cool thing is, you might think there's some nonlinear relationship. Turns out no. v1 prime and v2 prime will depend linearly on v1 and v2. How cool is that? Okay. How do we do that? First of all, let's put this m v1 prime on the left-hand side and this m v2 squared on the right-hand side. And same thing here, put all the v1s on the left-hand side and the v2s on the right-hand side. Then, what do we get? We get the following equations. So, let's now solve for v1 prime and v2 prime. So solve for v1 prime and v2 prime. Okay, so after we rearrange, we get the equations m v1 squared minus v1 prime squared equals capital M v2's prime squared minus v1 prime squared. Sorry, v2 squared. So yes, that is correct. It seems weird that there's opposite relation, but that is correct. And also from the momentum, we have m v1 minus v1 prime equals to capital M v2 prime minus v2. Now, here comes the cool thing. Let's take those two equations and divide this by this. Okay. Why are we doing this? Because here we have a difference of squares, and here we have a difference of numbers. But look, a squared minus b squared over a minus b, that's a minus b times a plus b over a minus b. We can cancel this out because supposedly the velocities change, right, after a collision. Otherwise, it's not a collision. And that just becomes a plus b. So, if you divide, the m's cancel out, and this becomes v1 plus v1 prime equals to v2 prime plus v2. And remember, we also have the momentum equation, which tells you this one, mv1 minus v1 prime equals to capital M v2 prime minus v2. Okay. And then let's see, one thing we can do, we can, for example, eliminate this v2 prime. So one thing we can do, we can subtract capital M times this equation from this equation. In other words, just like regular row reduction, let's multiply this equation by minus capital M and add it here. Then we get the following equation. Let's see. And by the way, here's the amazing thing. Here's where the squares disappear and we just get a linear equation. So, if you subtract, we get following equation. So, again, this is one part where linear algebra kicks in. You just row reduce, you solve your equations, then you get minus capital M plus M v1 minus capital M plus M v1 prime equals, now notice what's nice, here we have minus capital M v2 prime plus capital M v2 prime, so the v2 primes disappear, and that's just what we want. And we're left with minus 2m v2. And therefore, solving for this, we get v1 prime equals, so minus that over minus that, so we still have minus little m, capital M plus little m, over little m plus capital M v1 plus 2m over m plus capital M v2. I think that's correct, yeah. You put this on the right hand side, this on the left hand side, and you divide. And then just to make stuff a bit nicer, let's take all sides and divide it by capital M. So remember, for a fraction, you can sort of divide the numerator and the denominator, so it's okay. And we get minus 1 plus little m over capital M over little m over capital M plus 1 v1 plus 2 over little m over capital M. Sorry if they look alike, but this is like squarely plus 1 v2. And notice everything involves little m over capital M. So let's just call it R, like the ratio of the two masses, because it turns out the masses themselves don't matter, just the ratio of the two. So if this is R equals to little m over capital M, turns out you can just write it as minus 1 minus R over 1 plus R v1 plus 2 over 1 plus R v2. I think this minus, it makes stuff nicer at the end because we have 1 minus R. So here's a nice thing. Now we've explicitly written the velocity of the, I think, little object after the first collision in terms of the velocity of the first object, of the little object before the collision, and the velocity of the big mass before the collision. If you take this equation again, and multiply it by little m, then the v1 primes disappear, and you can write v2 prime in terms of the other equations. And if you're curious, let me tell you what you get. v2 prime equals 2r over 1 plus r v1 plus 1 minus r over 1 plus r v2. Oh, and by the way, here is why we use 1 minus r. R will be very small, so 1 minus r will be positive. If you use r minus 1, you get a negative number, which is quite ugly. All right, this is very good. We have two linear equations in terms of v1 and v2. Linear means you can put them in matrix form, so let's do that. So, in summary, if the big mass hits the little mass, then the velocities are related in the following sense. So, summary. We get that v1 prime and v2 prime equals minus 1 minus r over 1 plus r, 2r over 1 plus r, and 2 over 1 plus r, and 1 minus r over 1 plus r. R, you sure? Yes, I am. v1, v2. Where again, r is just the ratio of the little mass divided by the big mass. And again, this is for the collision when the big mass hits the little one. Okay? Maybe something like that. Okay? That's the first thing. So that's the first type of collision. But now you have to understand, once the little mass hits the big mass, then the little mass also needs to hit the wall. So now let's talk about the reflection at the wall. But this one is not too bad. Wall, because what happens at the wall? So we have this big mass here. It might move with velocity 2, and this little mass move, let's say, with velocity 1 towards the wall. The question is, what happens after it hits the wall? Well, since the wall has an infinite mass, turns out this doesn't change. So, in other words, the new velocity, v1 prime, is just minus v1. So, same velocity, different direction. And here, v2 prime is just v2. Because this one didn't hit anything, so the velocity is still the same. So in particular, we get v1 prime and v2 prime equals minus v1 and v2. And that's the same as the matrix minus 1, 0, 0, 1, v1, v2. So that just represents the whole collision with the wall. So the question is, maybe again, as a summary, if there's a collision between the two, we get this matrix. If there's a reflection at the wall, we have this matrix. Well, both are guaranteed to happen. So for every collision, there's also a wall collision. So how can we represent the whole thing? Well, you just compose the two. You're literally composing the two actions that happen here. And so, in particular, the whole process is then characterized by the following matrix. This is the beautiful thing in linear algebra. A matrix multiplication is the same thing as composition of linear transformations. In fact, I may talk about that today in lecture in linear algebra. So, step 3, the whole process. So, again, suppose the mass hits the big mass and then hits the wall. Then, at the end, the new velocity will be v1 prime and v2 prime, which is, again, first of all, the collision against the wall. So, minus 1 minus r over 1 plus r, 2 over 1 plus r, and 2r over 1 plus r, and 1 minus r over 1 plus r, v1, v2. So this is collision between little m and big M, and collision of little m and the wall, and we get minus 1, 0, 0, 1. So in the end, if you do the matrix multiplication, you get something kind of nice. 1 over 1 plus r, 1 minus r, minus 2, 2r, 1 minus r, v1, v2. v1 prime, v2 prime. So again, the setup is you have this little big mass moving, let's say, with velocity v2, v2, or maybe this way, sorry. So maybe v2, and then you have this little mass moving with velocity v1, and also the wall. And after the collision here, bang, bang, the new velocity becomes v1 prime and v2 prime, which might be different. And of course, they usually are. All right, so this is sort of one of the collisions, and then the question is then, what happens if this happens a bunch of times, n times? Well, the good news is, all you do, you just apply this n times. And again, this is a nice dynamical system, if you like. So after n times, maybe you'll see where we're getting at now. Because you may ask, why did we write it in matrix form? So far, you could just do it directly using algebra. So n times. The nice thing is, to repeat this process 8 times, you just have to multiply the matrix n times. So v1 prime and v2 prime, so n times, is just equal to 1 over 1 plus r, 1 minus r, 2r, minus 2, 1 minus r, to the nth power of v1, v2. And if you let that to be n, we just need to calculate a to the n. And remember, initially, we had the following assumptions. v1 was standing still, and the big mass was going to the left with velocity minus 1. So to calculate v1 prime and v2 prime after n collisions, all we need to do is calculate a to the n. And what time is this? Well, it's technically 6:25, but it's time to diagonalize. So step 4, diagonalize A. A equals to PDP inverse. Okay, so in other words, find a diagonal matrix D and an invertible matrix P, such that A is PDP inverse. Well, let's see. A is 1 over 1 plus R times 1 minus R minus 2, 2R, 1 minus R. And here's the neat thing, to find, the eigenvalues of A, because we want to set a determinant equal to 0, turns out this factor doesn't matter. So it's enough just to do lambda I minus A, if you want, which becomes 1 over 1 plus R, and then lambda minus 1 minus R, 2 minus 2R, and lambda minus 1 minus r. And you want to set that equal to 0, so this 1 plus r just cancels out. Lambda minus 1 minus r squared plus 4r equals 0. And so this is positive, so we get negative, so we take square roots, and we get lambda minus 1 minus r equals to plus or minus 2 square root of ri. And so lambda is just 1 minus r plus or minus 2 squared of ri. And let's call this lambda plus minus. Plus for the positive imaginary unit and minus for the negative imaginary unit. Then just sketching it, so if lambda is in fact 1 minus r plus 2 squared of ri, you take the null space of lambda I minus a, which in this case, notice the 1 minus r's, it would cancel out, so it's really just a null space of 2 root ri and 2 and minus 2r 2 root ri, and that equals to the null space of, let's first divide the second equation by minus 2r, so 1 and minus I over root r. And here's the nice thing, you know this matrix is not invertible because by definition of an eigenvalue. So in particular, the only way it could be non-invertible is if the first row is also equal to that. And indeed, that is true. And if you try to find the null space, what combination makes this 0? Well, it's just if here you put I over square root of r and the other one 1. So this is one eigenvector, and the question is, how can you find the other eigenvector? The nice thing is, you just take the conjugate. So if v is an eigenvector to lambda, v bar is an eigenvector to minus lambda, so v bar is an eigenvector to lambda bar, so we get minus I over square root of r1. Two eigenvalues that walk into a bar. Hopefully they're complex, otherwise there's a collision, which is nice in this video. Okay, good, so back to math. So then what did we get? So in fact, A equals to PDP inverse, where D is the matrix of eigenvalues and P is the matrix of eigenvectors. So here's again where the linear algebra kicked in. So A equals to PDP inverse, and D equals to, if you want, 1 minus r minus 2 square root of ri over 1 plus r, 0, 0, and then 1 minus r plus 2 square root of ri over 1 plus r. And it doesn't matter which order you put this in, as long as your eigenvectors have the correct order. So here P would be minus I over square root of r and 1, and I over square root of r and 1. And if you do the calculation, you can also find P inverse is then just I squared r over 2, 1/2, and then minus I square root of r over 2 and 1/2. Okay, so we have that, and notice how ugly D is. In particular, calculate the nth power of D. It's very messy with this formulation. That said, it turns out if you write this as a complex exponential, it's much easier. So let's actually do that. So note. So write lambda plus minus in the form r e to the I theta. And again, this is to simplify our work. So note. Write lambda plus minus as r e to the I theta. Then, so what is r? So again, first of all, lambda plus minus, remember it was 1 over 1 plus r, then 1 minus r plus minus 2i square root of r. Well, then, to get the radius, so the little big r, you just take the modulus. So r equals to lambda plus minus. And it's not clear that they have the same modulus, but it turns out yes. And to find this, it's just 1 over 1 plus r times the modulus of 1 minus r plus or minus 2I squared of r. And then, here's a beautiful thing. 1 over 1 plus r, this becomes square root, the real part squared, 1 minus r squared, plus the imaginary part squared, so 4r. Looks like a lost cause, but let's persevere. So we get r squared minus 2r plus 1 plus 4r, and that's 1 over 1 plus r square root of, maybe you see it already, r squared plus 2r plus 1, which turns out is a square, so 1 plus r square root of r plus 1 squared, which just becomes 1 over 1 plus r times 1 plus r. This cancels out, and in the end you get 1. So turns out the modulus of our eigenvalue is just 1. So maybe there's some esoteric way of finding it using, I don't know, unitary matrices or something, but I think this is pretty neat. So this is true, and then, therefore, what does it say? So by the way, just another fact, if z equals to x plus iy, and that's equal to r e to the I theta, we just calculated that r is square root of x squared plus y squared, and then theta, turns out you can calculate it as arctangent of y over x. So lambda plus, which is 1 minus r plus 2 square root of ri. We just calculated the modulus to be 1, so it's just 1 times ei arctangent of, so 2 square root of r over 1 minus r. And if you let that to be theta, then it just becomes e to the I theta. ei theta. And same thing with lambda minus, that's 1 minus r minus 2 square root of ri, that's ei arctangent of minus that, minus 2 square root of r over 1 minus r. And if you compare it, arctangent of minus x is minus arctangent of x, so literally this becomes e to the minus ri theta. So that's really good, because then A equals to PDP inverse, and that's equal to P e to the I theta, 0, 0, e to the minus I theta, P inverse. So it's e to the minus I theta and plus I theta. So A is PDP inverse, which is P e to the minus I theta, 0, 0, e to the I theta, P inverse. And therefore, the reason we did that, now it's very nice to calculate a to the nth power. So a to the n is then p. You raise this to the nth power, e to the minus n I n theta, if you want. 0, 0, e to the I n theta. So in general, it would have been hard, but now it's easy. P inverse. And remember, we had our explicit values for P and P inverse. So if you multiply those three matrices, turns out you get a nice simplification. And I'm not going to do it, because otherwise it would take 2 hours instead of probably 1 hour. So if you do the multiplication, so as time goes by, you get cosine of n theta, square root of r sine of n theta, minus sine of n theta, over square root of r, and cosine of n theta. So this is a to the n. And well, how does that solve our problem? Well, now we have an expression for the collision after n times. Because all it is, you take this matrix, remember it was a to the n times 0 minus 1, but now we have our matrix times 0 minus 1, and this just tells, take this column but multiply it by minus 1, and we get sine of n theta over square root of r and minus cosine of n theta. Okay. All right, we're sort of almost done. So we're at our last third, if we want, because this is good. So we calculated the velocities after n collisions. And now what do we want? We really want to find n such that eventually the second one, so the big mass, has a bigger velocity than the first mass. So what is the ending condition? So let me redraw a little picture. Remember what we tried to find. So we had the big mass here with velocity v2. Maybe moves here. And then the small mass with velocity v1. And well, they collide many times until this one eventually moves to the right much faster so that the little mass cannot even keep track of it. And so really the ending condition is just v2 is greater than v1. Now, I would like to remind you we just found v1 prime and v2 prime to be sine of n theta over square root of r and minus cosine of n theta. So really, and now ignore the prime, so we want to figure out after how many collisions this is bigger than that one. So goal, find n such that v2 is greater than v1. In other words, minus cosine of n theta. It's greater than sine of n theta over square root of r. If you cross multiply and put this on the right hand side, this is the same thing as saying 0 is greater than square root of r cosine of n theta. So minus square root of r cosine of n theta to the right hand side becomes positive, and plus sine of n theta. Okay, now notice in general this is kind of hard to determine. After this, we'll just, turns out there's a simplification to this, and it's based on a little ingenious calculus trick. And you'll see why. And turns out you can also write it in terms of tangent, but I think this one is way cooler. So take this equation here and multiply both sides by square root of 1 plus r. So it turns out this you can also write as square root of 1 plus r, square root of r over square root of 1 plus r, cosine of n theta, plus 1 over square root of 1 plus r, sine of n theta. Why did I do this? Because consider the following triangle. We have the right triangle with, let's say, adjacent is 1 and this is alpha, and this side being square root of r. Then, by the Pythagorean theorem, this side is 1 squared plus square root of r squared, which is 1 plus r. And notice, this is precisely sine of alpha. So square root of 1 plus r, sine of alpha, cosine of theta. And this is cosine of alpha, n theta. So cosine of alpha, sine of n theta. But that's precisely the sum of sines. So square root of 1 plus r, sine of alpha plus n theta. And remember, what do we want? So first, also one little thing, because we want to write it in terms of alpha. So notice, what do we have? So for example, the tangent of alpha So the only thing left, we did cosine, we did sine. Tangent is square root of r over 1. So alpha is just arctangent of square root of r. So we have sine of arctangent of square root of r plus n theta. And remember what we want? We want this to be negative. Right? Remember, 0 is greater than that, so we want this to be negative. So notice this is positive, so this just cancels out. And now let's talk a bit about sine. So sine is positive and then becomes negative from pi to 2 pi. And remember, of course, after a huge number of collisions, the big mass just goes away. So really what we want the smallest number of collisions. And the smallest number that makes sine negative is at least if the number is greater than pi. So ideally, we would like this angle to be greater than pi. So since we have the smallest number of collisions, we want this to be greater than pi. So since smallest number of collisions, we need arctangent of square root of r plus n theta to be greater than pi. And now, remember, our goal was to solve for n. So we just get n is greater than pi minus arctangent of the square root of r over theta. Now, a long time ago, when we wrote our eigenvalues as complex exponentials, we found that theta was just also an arctangent. So this is pi minus arctangent of square root of r over arctangent of 2 square root of r over 1 minus r. And so far we've been rigorous. Now we want to use sort of our applied math hat, and we want to use the fact that arctangent of x is very close to x. And this is true if this number is kind of small. And therefore, this is roughly equal to pi minus square root of r over 2 square root of r times 1 minus r over 1 minus r. And by the way, it's okay that we just use an approximation, because remember, we want n to be an integer, so it's okay. So if there's an error of 0.001, since we want the biggest integer, doesn't matter if there's a small error. So, and then we get 1 minus r times pi minus square root of r over 2 square root of r, which you can just separate this, and you get 1 minus r times pi over 2. Pi over 2 square root of r minus 1/2. And lastly, so r will be very small, so 1 minus r will be roughly equal to 1. And again, I know it sounds very engineering-y, but again, we just want an integer. We don't care if the error is like super small. So at the end, we get that our n has to be greater than pi over 2 square root of r minus 1/2. So, last but not least, so let me write that down. So, n, in other words, how many times do we have to repeat this whole process? Well, pi over square root of r minus 1/2 times. So n, want n to be bigger than pi over 2 square root of r minus 1/2. Okay, now, what is r? Remember, r was the ratio of the little mass divided by the small mass. Again, to reiterate, so we want the number of processes to be bigger than pi over 2 square root of r minus 1/2, where r is the ratio of the masses. Now, let's choose a specific ratio. So step 6, choose because usually the ratio is small. Of what magnitude is it? So choose r to be 100 to the minus k, where k is to be determined, and you will have a beautiful formula that comes out of this. Okay? Now, remember n is the number of processes. And by process, I mean the following. I mean the big block colliding on the smaller block, so one collision, and the smaller block hitting the wall, so two collisions. In other words, how do you get the number of collisions from the number of processes? It's just 2 times that. So n collisions equals to n plus n. So collision of masses. And this is collision of wall. Well, and that is indeed 2n. And we want this to be bigger than 2 times pi over 2 squared of r minus 1/2, which becomes pi over square root of 100 minus k minus 1. And now, 1 over square root of 100 minus k, it's square root of 100 to the k, and it's square root of 100 to the k, and it's 10 to the k. So we indeed get pi times 10 to the k minus 1. All right, we want the number of collisions to be bigger than pi to the 10 to the k minus 1. In general, this is not an integer, but because we want the smallest integer bigger than pi to the 10 to the k minus 1, we have to take the ceiling function, because the ceiling function is the smallest integer greater than a certain real number. So step 7, the number of collisions, which is the thing we're asking at the very beginning, is the ceiling of pi to the 10 to the k minus 1. And in general, the ceiling minus 1 is not a floor, because this could be an integer, but because this is not an integer, the ceiling minus 1 is indeed the floor. So pi has the floor today. So the answer is floor of pi times 10 to the k, and let's see what that equals to. So if k equals to 0, and remember, r was 10 to the minus k, which is m over m. So if the two masses are the same, then the answer becomes pi minus the floor of pi. I like this notation, floor, ceiling, I don't know what this looks like. So it's the floor of pi times 10 to the 0, which is floor of pi, and pi is 3.1415. If you take the floor, you get 3, the first digit of pi. If k equals to 1, you get the floor of 10 pi. And that becomes 31.4 ... The floor of that is 31. The first 2 digits of pi. If k equals 2, we get the floor of 100 pies, which is... It sounds like me baking pies and making an accident and all the pies on the floor. Yeah, it's the floor of 100 pies. It's my misery. Then we get 314.15 ... The floor of that is 314. And in particular, you can just continue, and in the end, if you do it infinitely many times, you get all the digits of pi. So surprisingly, in this problem, the digits of pi appear. So how cool is that? And that's really the definition, if you want, of digits of pi. And you may ask, well, where did it appear? Well, in this calculation, because remember, we wanted sort of the sign of something to be negative, and the smallest value after which sign is negative is precisely pi. That's how this pi appears. So how cool is that? And we get the 10 appears from this 10 to the minus k. So really, really, really neat, I think. So, oh, that was 100 minus k, but anyway. So really neat idea. I would like to thank, first of all, 3 Blue 1 Brown for coming up with the idea. I thought it was really sweet. And also thank you Tobias Schmale for this wonderful proof using just linear algebra and not really geometry, so that's nice. Alright, so if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much. Oh, an hour. Impressive.